right, it's rolling.
There's one thing I want to do before I address Zach's question, statement earlier. As advertised last Thursday, the relationship between temperature and kinetic energy. Because I've talked in class about, energy being transferred into a particle, something that or a slided object on the surface, and the energy lost by the object gets transferred to the surface, and the surface heats up a little bit. So there is a connection, and the math for the derivation is definitely accessible for you. There's a non-calculus based derivation of it, but I figured you deserve the best. And I need to figure out what I did with all that stuff. That's not it. Oh, like that. All right, so I have a container, and we'll make it rectangular. Rectangular solid, except it's hollow inside. And there's a bunch of gas particles in there. So I have in gas particles. Each particle has a mass m. So I want to figure out how much force is exerted against, we'll just say this side right here, and we'll set up a coordinate system. X, Y, and Z. And so if I think about sort of a side view of it, I have a particle that comes in, it's going to hit here and then bounce off. We are making the assumption that is a perfectly elastic collision. So the wall is not going to absorb any energy in this transfer. And if I think about it, I've got this thing coming in with some initial velocity, and then it leaves with some final velocity. If energy is not lost by the particle, then the initial speed and the final speed are the same. I'm not worried about any potential energy considerations here. So I got 1/2 mvi squared equals 1/2 mvf squared. So I also know that P initial is equal to P final. So mv initial equals mv final. Actually, that last bit right there, let's redo that one. Momentum can't be the same before and afterwards. Why not?
Because they're going in a different direction.
Absolutely.
I don't know how to do that.
Can't hide genius. So if I break this up into components here, I've got some Vy component and a Vx component. Let's just go with traditional I, J, X, oh, sorry, that should be a Y there, and that should be a Z. Otherwise, the way I had it was a left-handed coordinate system. I hat, J hat, Z hat, K hat. So my initial velocity, or actual throw mass into it, my initial momentum, is of the particle, with a little p there for particle, is going to be Vx I hat minus Vy j hat. My P final for the particle, and V final, leaving all sorts of stuff out of it. This excited about getting to the end. All right, not for the end's sake, but because of the formula. So this is mv, negative mvx I hat minus mvy j hat. Again, given this coordinate system right here, in the way I've broken up the x and vy. Questions up to here?
Why do you need to break up the particle bouncing into I hat and j hat?
Because what I really care about is the change in momentum. And so it's easier to do it this way, since I didn't give you an angle. Speaking of which, what is the change of momentum called?
Impulse.
All right. So that's going to be equal to the impulse, which I think I used I with a vector symbol over it before. It's just going to be P final minus P initial. So this would be the impulse on the particle. And so I've got my breakdown over there. So I've got negative mvx I hat minus mvy j hat minus mvx I hat minus mvy j hat. Which simplifies into
Negative 2 mvx I hat.
so that is the impulse on the particle. Therefore, what is the impulse on the wall?
Positive 2.
Yeah. So we have this impulse on the wall from the particle of positive 2 mvx I hat. So this would be it for a single particle. So we'll just sort of write that note in the margin over here for a single particle. But obviously, if I've got a box full of gas, then I'm going to have a whole bunch of particles, so we need to adjust for that.
Right.
So questions on here before we adjust for having multiple particles?
Okay.
And what we have here is superposition of waves. We've got, basically it's a standing wave. You see the two waves passing through each other. Nothing to do with what I'm talking about over there, but related to what we talked about last week. And that's not the one I want.
No. Oh.
There we go. All right. So I'm making the assumption that we have a whole bunch of particles in there, and that in the entire box we have n particles. Oh, which I wrote over there, number of particles in the box. And V is the volume of the box. I'm making the assumption that it's a uniform distribution, which is a reasonable assumption unless you're dealing with something so large where gravitational forces start to matter. But I am making the assumption that N over V is uniform. So the particle density is uniform, another way of saying the exact same thing. If I'm trying to figure out, I have these particles hitting the side here, I know that at any moment in time, I'm not going to have every particle hitting the wall at the same time. Or it's so statistically rare that not worth looking at. So what I'm going to do is I'm going to look at all the particles that will hit the wall within an infinitesimal amount of time, dt. So in order to hit it, I've got this small little region right here, which I'm just going to label as dx. The area of this side right here, I'm just going to label it as A. So the volume of the area where particles can actually, within, say, the next amount of time of dt, the amount of particles that can hit it would have to come from this area here. And so dV is just the volume that contains particles that will hit the wall within the next infinitesimally small amount of time. And that's just going to be A dx.
Area of that wall.
Yeah, of that small little sliver right next to the wall.
Oh.
And as a matter of fact, we can narrow it down to slightly more. The volume of this within this infinitesimal amount of time would be A times Vx dt. So if I just have a fraction of a second, the only particles can hit the wall that are traveling at some speed Vx that will hit the wall within an amount of time dt. That's just as far as they can travel. Now, since this is uniform, this will be dn over dv, where dn is the number of particles in my blacked out region over there. So dn, the number of particles, would just be the total number of particles in the box divided by the total volume of the box times dv.
Oh, so AVX?
Or that one,
Or that one, yeah. Yeah.
which would be n over v a dx dt.
What is dV?
dV is the volume of this infinitesimally thin little piece of the box in which the particles would actually hit the wall within the next small little change in time.
Okay, thank you.
Okay. This is like a setup to get the, what I'm guessing is we're integrating the time at some point. We're gonna-
We actually won't do any integration here, but yeah, we're throwing integration into it is unnecessary. I'll put it that way. All right, so this would be the number of particles that is actually going to hit the wall. It's some tiny amount. I know each particle hitting the wall is going to exert that much impulse. So the total impulse that's hitting the wall, or the total impulse applied to the wall, is just going to be that times the number of particles that do it.
So it's that times dn.
Yep. And so the total impulse is going to be, and then mathematically, I guess it would be the differential there, di. It's going to be 2m dx times n over v a dx dt. By divide by dt.
Is it,
Beg pardon?
so you do multiply the MDX on there too?
Yeah, because the impulse has, it's 2m dx. Now, we do have to make one adjustment that sort of hand wave through, because what I've done here is I have the number of particles that are traveling at this Vx that are going to be able to hit the wall, except I haven't accounted for the fact that I might have one particle going 50 meters per second that way and another one going 50 meters per second the other way. Statistically, only half the particles are actually have any component in that direction. So we have to divide by 2 to account for the fact that half of them are going in the other direction. So I now have mvx squared n over v that leaves with something there. I got the m, the vx squared. I think I got it all. This impulse is just f dt.
What is it, F? Is that just like force?
Yeah.
Oh.
It's the force that the wall exerts on the particle, or the particle force, actually in this case, officially it's the force that the particle exerts on the wall.
Oh.
DT's cancel out, so that's why we don't have to integrate. And so I'm left with force is equal to mvx squared n over the volume times the area.
That's not that bad.
I'm going to divide by the area. So I'll have force divided by area. So this is, we have this total force that's being exerted on the wall divided by the area of the wall. And I'm not quite sure how far over before the camera stops picking it up. So we'll pass this. But if I divide by the area, so I force divided by area, what do I have?
Wait, density. No?
Not force divided by area, it's
gosh.
not density.
Oh gosh, I've wondered.
Pressure?
Yes.
Pressure, yeah,
It's
that
pressure.
one. It was either density or pressure in my mind.
Pressure?
Force per unit area. This P right here is for pressure. I don't have a vector symbol over it. I'm not talking about momentum here. And so we are left with, and change the order slightly, N over V mvx squared. Now hopefully you can start to see some formation of something kind of related to kinetic energy. The formula that all of you know. However, the kinetic energy of a particle depends upon not the speed in a particular direction, but the speed. So if the actual velocity of an object is vx I hat plus vy j hat plus vz k hat, we do a dot product with itself. We get speed squared on the left, and over here we just get vx squared plus vy squared plus vz squared. And if I'm looking at average values, and I'm just going to use this symbol, putting it into the less than, greater than symbol, is the equivalent of just saying average. Similar to putting a bar over the top or writing AVG as a subscript. That's going to be the average of vx squared plus the average of vy squared. That squared should be inside. Plus the average of vz squared. Questions here?
Why are we averaging? Is it like we have multiple values? Like,
Where are we heading?
no. Why are we averaging?
Because in the end, I'm trying to figure out, this is the pressure, and I'm basically morphing this into average. The average pressure.
Okay.
I was going to hand wave across that, but we'll throw the step in. Because these particles are moving around randomly, there's no reason to think that any one of these would have dominance. It would make sense that the average in the x direction is the same average in the y direction as in the z direction. In other words, all of these, each of these, I should say, are the same. So the average speed squared should just be 3 times the average speed in the x direction squared. So this is, so Vx squared average is just V squared divided by 3. So I got N over V. Put the 1/3 out front. M average speed squared.
Sorry, how did we get the 3 times Vx squared?
I'm making the claim that the particles inside this box, there's a whole bunch of them, and they're moving around randomly with no particular orientation. That it's just as likely to be moving this way as that way, as that way, as that way. In any direction, it's just as likely to move in any direction. So the average value of the x components, and plus the average value of the y components, plus the average value of the z components, each of them squared, would be the same. That average and that average and that average are all the same.
Oh.
And therefore, if the averages are all the same, then this adds up to just 3 times one of them. And since I have the x over here, I choose the x.
Okay, thank you. That makes more sense.
And it is the average of the speed squared. If it were just average of Vx, then it would be 0.
Okay. Because in this problem, we only have Vx.
Yeah, I started just looking at one wall here.
Right. So that's why we're doing the 3 times Vx squared.
Yes.
Because
Because I got
But if we had another problem and you gave us all 3 directions, it would just be Vx squared plus Vy, like how you have it there. If we were
If
given,
these were not all the same,
yeah,
then we would,
no, I think I get where you're going.
if they're not all the same, I think we would have to start out in a 3-dimensional problem as opposed to a 1-dimensional and then jumping to 3.
No.
Surely the derivation's out there somewhere. I haven't seen it. I got the simple one. I thought, hey, you know, I'm good with that.
Alright, cool. So
Alright.
1/3 n